In the video we're going to review what we already know from last time about gradient function and link that to the idea of curve sketching, which we've seen a bit in the past. So this is a review video, and basically we've got to remember a key fact to begin with. The derivative of a function is basically a function of the slope of all the tangents of the original graph, and we also call the gradient of the function at that point the slope of the tangent. Okay, and the slopes all together, if you had that infinitely many slopes, you'd create another function, and that would be called the gradient function of that original function. So that is from previous work. So if we had, because we're taking the derivative to find that, we basically, if we started with some sort of cubic, the gradient function would be some sort of quadratic, and so on. So the degree of the polynomial, if it is a polynomial, will go down by 1, okay? Go down by positive 1. In other words, it'll be 1 less, to make that nice and clear. Now if we talk about maxima and minima on the original function, that's when the gradient equals 0, and we can find out when the gradient function equals 0 for that. And for that to happen, the original function must have zeros. It must basically cut through the x-axis, so it must have x-intercepts. Okay, so if the original has a max or a min, that means it has a place or places where the gradient is 0 and the gradient function cuts the x-axis because its y value will be 0. So if the original function was like this green line, that means it's got a positive gradient. Its gradient function will be above the x-axis, okay, because that's when its y value is positive, and when the original function is falling or has a negative gradient, it will be below, in that interval, it will be below the x-axis because its gradient is negative. So there's some key things. Let's have a look at it in action now. If we follow these directions on the graph we've got here, the purple graph is the original graph, and what we've got to do is sketch the gradient function and comment on the domain and range of the gradient function. Okay, so we've got to sketch the gradient function and discuss its domain and its range. So there's the original, and we can see a few features on there. One key feature is that it's always falling, this purple graph. So its gradient is always negative, okay? It's not constant, but it's falling. It also has 2 asymptotes. So 2 discontinuities there, which does some fascinating things to the gradient. So if we have a look now at a shrunk down version so we can see the entire thing, we can reason what they've done, reason it through. So you notice that it's always falling, means that the gradient is always negative, so the gradient function will always be under the x-axis, so the whole time it's in the negative, so that's reasonable. We know that this is falling, but it's falling more steeply here and here and here, and the logical extension, if it were able to reach the asymptote, which it can't, it would be vertical there, which would have an infinitely large in the negative sense gradient. So you could consider its gradient as approaching negative infinity. So that makes sense there. If we look at this graph, it's doing it in a gradual curvy sort of way. That's not a mathematical term, curvy, but it's doing it in a gradual way, and you can see that the gradient function follows likewise too, where the gradient here is almost it's almost 0 there, so you can see around that interval there that the gradient function is almost at y equals 0. So it's decreasing, or its magnitude is increasing in the negative sense. It will approach the same asymptotes because this here will keep going down and it won't reach that. So there's no function at the point, therefore there is no gradient either, no defined gradient, because there's no defined function at the asymptotes. So it's interesting there. So if we look at the other side of the asymptote too, that as it approaches the asymptote, if we go backwards to approach the asymptote, it would become again infinitely steep downwards, and so this is coming from that there as we go across to larger values of x. This here, its gradient is negative but becoming less so, and that's why the gradient function is getting less negative. It's heading towards that axis, but it doesn't quite reach it. That's not a horizontal inflection. Okay, that is not a horizontal inflection. You can see that there's a slight slope, so it is in the negative, so that is a small negative value there for the gradient function. And the same behavior occurs for the second asymptote as for the first one. So let's look at the domain and range of the gradient function. The domain of the gradient function is real numbers except for 2 values. Now, of course, this is a bit of an abstract question. There are no actual values given except for basically the x values that correspond with the asymptotes. So it's got those two discontinuities, but it can be any real number apart from that, as you can see. The range, or possible y values, are all negative real numbers, because the ultimate extent of this would be to approach 0, but it won't approach it, so it'll go down to basically 0, but not including. It'll be an open set. It won't include 0, so it'll be basically so in other words, all of the range, if we're going to use y, I think it was d of x above, but anyway, because that says y, I'll use y. Y is all values greater than 0, sorry, less than 0, my apologies, because it's negative, so not including 0, less than 0, okay, so all negative real numbers. Okay, that will keep approaching, that gradient will keep approaching 0 without getting there, and this will approach 0 in its y values without actually getting there. And the same occurs on the other end.